Well, welcome everybody. Thanks for coming out to hear our talk. Rajesh and I are going to be sharing some experiences with you. I realized I'm trying to condense about 18 months of migration work and a lifetime of monitoring experience into about 40 minutes. But bear with us as we try to run through this, and hopefully there'll be some time for questions. So just to kick it off, my name is Toman. I run infrastructure engineering at Planet. Some of the coolest work I've ever done and some of the least interesting work at Planet, which I'll talk a little bit more about the cool stuff that we do, but my background has been sort of in infrastructure and clouds for quite some time. As for Planet, we are actually imaging the Earth on a daily basis. So our first mission as a company has been to be able to capture the landmass of the Earth every day, which amounts to about 1.5 million 29 megapixel images, covering about 350 million square kilometers. That's over 6 terabytes of data every day forever that we have to manage. The other interesting thing is that most people want to look at pictures of the Earth that don't have clouds. So I have a really different cloud problem than you've heard about for most of the people here, but we'll dive into that a little bit as we go through this.
So hi everyone, my name is Rajesh. I'm the chief architect at SignalFx. I joined SignalFx a little bit over 5 years ago now. I joined as part of the founding team. And I've been over there working mostly on our streaming analytics engine, which we'll get to know a little bit about going forward. Prior to SignalFx, I was at Facebook for about 4 years working on cluster management and monitoring related projects. And prior to Facebook, I was at Google for several years, again working on like cluster management type software. So a little bit about SignalFx. So SignalFx is a monitoring and operational intelligence solution. We help people understand their cloud environments. We take data from these cloud environments, be they from infrastructure or from application, from other services that you might be using. Bring that data into SignalFx and process it at very, very low latency, real-time analytics and anomaly detection for people to really get insight into what's happening in their system. And we're very pleased to have Planet as one of our customers since 2017. And we are very happy to share the story that we are going to have now with Troy. So what we're going to talk about today is about Planet, primarily all the cool problems that they solve, all the infrastructure that they use, the problems that they face in trying to solve these complicated image processing, and how and when they manage to kind of do their migration from their legacy environment into GCP. I'll chip in a little bit about things to think about when you're planning a migration such as this, what kind of monitoring and observability you need to have in place to have a successful migration, and then to continue to operate your environment successfully post-migration. So Troy, you want to take it away?
So just to give you some context, as I mentioned before, our kind of initial mission in the world was to try to capture the Earth every day and make that accessible to as many people as we possibly could. We're now kind of moving. We've accomplished that first mission. We're getting the daily imagery of the planet, but now we're kind of moving up the stack and realizing that what people want is actually data and information, not just pictures. And so they don't actually want a picture of every spot on the Earth every day. They want to know, where there are buildings, where there are roads, when things are changing, when disasters have struck. And so increasingly, we're starting to build an analytics layer on top of our data engine and feeding that into our customers. So our platform or the stack, when we talk about full stack, it goes all the way from embedded computers that are flying 500 kilometers above the Earth to we build and run our own ground stations. We obviously have to store and manage and process tens of terabytes of data every single day. And then that all feeds back through our user system. We do that mostly on the Google Cloud today. It starts out with about 150 operational satellites, the largest operational constellation in the world. We have, I think, over a dozen, maybe close to 20 ground stations around the world that receive the data. We upload that into the cloud. We have tens of thousands of VMs that sit in Google Cloud that crunch on that data, and then an API and sort of series of ways for people to access that information. To kind of dive down a little bit more, from a software perspective, this data comes into our processing engine. So this is all the stuff that kind of happens now in GCP, but you'll hear me talk a little bit about our data pipeline, which is where we started. And that really is about getting our imagery and doing all of the work that has to be done to make that usable by customers. For example, when you take an image of the Earth, you've got a 2D image of what's fundamentally a 3D surface. And we have to take and essentially map every pixel that we take from space onto a physical location on the Earth because we want accuracy within 3 meters. So we have to know, you can have slightly off telemetry in space that can cause you to be 50 to 100 miles off of where you thought you were of the Earth. So there's a whole set of processing that has to go to make that useful to our customers. And then it turns out everybody wants it in different format. People want web tiles, people want analytic products, people want beautiful images that look good, that are maybe stitched together of mosaics of lots of different images together. And so all that sort of number crunching goes on in the background of our platform. So we do this. I think we have somewhere between 50 and 100 software engineers spread around the company. And we're located, our headquarters is here in San Francisco. We have a large office in Mountain View, but we also have offices in Canada, Texas, Berlin, and remote employees sort of spread worldwide. So it's a very distributed environment. Our development work is mostly in Python. Historically, we were doing a lot more with Go, with new pieces, and then a lot of our front-end work is JavaScript-based. We are entirely cloud-based. We have almost no on-prem hardware. And what I'm going to talk to you about is a lot of our stuff started in AWS. We still have some things there. Some things will always remain there because of regulatory requirements that we need GovCloud. But we, about 18 months ago, began a process of migrating to Google. And I'm just going to tell you a little bit of the things we learned during that process. So a timeline, I realized we already have one inconsistency in our slides. We sort of talked about integrating with SignalFx in 2016, and you said in 2017, but we've been with SignalFx sort of embedded in our infrastructure very early. And the big thing for us is really this marking point of launching our 80 satellites, our first production set of satellites in January of 2017. And we knew that we needed our cloud choice was going to become kind of permanent around that time frame. Because once we started actually downloading 1.5 million pictures a day, we weren't going to move a lot. And as it was, we had a lot of data to move. So we kind of began our evaluation process around here. We started our first phase migration in December, and then actually flipped live before the last Next conference in San Francisco, which was actually in March of 2017. And then we've kind of kept our phase 2 migration going over the last 18 months or so since then. And I'll walk you through some of our experiences, but this gives you a general idea of the flow. So why did we end up on Google after we did our analysis? There were a couple different things. First of all, we really felt there was a good product fit. A lot of the network and storage capacity pieces lined up with a lot of the data requirements that we had. We particularly liked the ability to use predictable VMs, or preemptible VMs, which have predictable pricing versus things like spot markets on AWS, where the market fluctuations were difficult for us to manage. The pricing model felt very natural for sort of where we came from, this sort of bursty, images sort of flow in and out. We're bursting up and down, and it flowed well for that. And we also have, there are a lot of, if you've been around the conference, there have been other geospatial data providers talking, but there's a community of geospatial data providers. There's a lot of new geospatial features coming out in BigQuery and other platforms, and it just felt like a good fit from a market fit. We also, interestingly enough, acquired Terabella, which was the T in the Alphabet product line of Google. Their satellite business is actually in a part of Planet now, and so we have other strategic relationships that have made sense for us. And we also, I guess the last thing I would say is their commitment to open source technologies, particularly in Kubernetes and some other things, lined up well with how we wanted to grow and do things at Planet. So we did a 2-phase migration at Planet. Because all of those satellites were going up and we were going to start getting rained down with SatDat in last year, we made a decision to get that moved as quickly as possible. I was looking at one of the slides beforehand where it was talking about Evernote moving 3.5 petabytes of data over a 7-day period. We moved 7.5 petabytes in under 30 days. Which I'll talk a little bit about some learnings from that. But that was a big chunk of the move. But we also ended up moving about 40,000 servers worth of work from one cloud to the other in that same sort of 70 to 90-day window. So I'll talk a little bit about kind of the things we learned and where we end up. We took the rest of our, we had a lot of merging applications that were more customer-facing and less heavily trafficked, and we actually did some work to kind of refactor those, move them into containers in Kubernetes, and migrate them to Google later. Some things worked good about that, some things not quite so good, and I'll talk about some of the trade-offs there. But that process is actually still ongoing, and it's kind of dragged out as we've needed it to over the course of the last period of time. So in that first, if you look at our overall environment today, some key tools that we use for automation and tooling, we tie into GitHub and GitLab. We use their automation environment. We're heavily bet on sort of containers as a mechanism for deploying apps. Jenkins and Ansible, probably other two kind of heavy automation tools. Then we have our pipeline. We're not very imaginative at naming things, so we have a company named Planet, we have an application named Storage, we have another application named Jobs, and I'll talk about those. And then we kind of have our API services platform that's Kubernetes-based that has moved over since then. So I talked about a few of these pieces, but I think what I want to say is that the automation that we had invested in made the migration much easier, and we intentionally decided not to change a lot of that when we moved to Google. So obviously we had to do some things where we had to take Ansible abstractions for AWS and substitute them with Ansible abstractions for Google. We had to go do a few even commits to upstream. I think I did a commit to Packer to support some advanced Google Cloud features because we are crazy people that like to use stuff in alpha on Google Cloud, and which I'll tell a story about that later. But but those open source tools were there, and we leveraged them heavily to get to move forward on the platform as we went. And it really served as a pretty strong foundation for making the migration go relatively quickly. So the phase one piece was the storage and imagery platform, and so we moved storage over. It consists largely of all the imagery is stored in GCS. Just as images, so we don't do any special sort of database for those images. We store the blobs in GCS. The sort of secret sauce, I guess, comes into play with how we manage all the metadata. So we keep track of which satellite it came from, where we took the picture, what rectification coefficients we need, what color curves we've applied to the image, all that type of data over the history of the lifetime we keep, and that used to be stored in a Postgres database, primarily because of PostGIS, which is the geospatial information extensions to Postgres. And so we moved a 20 terabyte, I think a 10 or 20 terabyte Postgres database over in the process. Since we've been on Google, that we then migrated a lot of that metadata out of Postgres into Bigtable, but we did that as a two-step process that worked very well for us, and I'll talk about that. Our jobs platform really is just a batch queuing platform that manages a pool of VMs. And I'll give you an idea of what that pool looks like and how we've scaled that over time. And then phase two, which is what we're in the middle of now, is really all of our container-based services. So we moved all of these public-facing APIs into containers, onto Kubernetes, self-hosted Kubernetes on AWS. And then what we've done is built a similar platform on Google, and then allowed people to basically repoint their deployments from a Kubernetes environment in AWS to a Kubernetes environment in Google. We also make heavy use of Cloud SQL, mostly Postgres, well, we have a lot of Elasticsearch in here, but I don't want to talk about that because anybody that does operations probably doesn't like to talk about Elasticsearch. I'll answer questions if you want, but we do have a couple of very large Elasticsearch backends for all of this as well. So with that in mind, of kind of the background of what we did, I'm going to let Rajesh talk a bit about some of the monitoring ideas that I think we both have a philosophy for, but he has way more experience with.
Thank you, Troy. So I'd like to talk a little bit about how you go about monitoring something as complicated as migrating from one environment to another. But the first thing I want to raise is that when you're considering such a large change, you should really think strategically about monitoring. So obviously, making a change in cloud environments is a big change. But if you think about it over the life cycle of your entire service or your entire product, that's only one of the changes that your system has to be able to handle. You'll obviously be making changes to various kinds of implementations, various kinds of architectures, new builds, even things like configuration changes. And these are all things that you'll have to kind of be able to monitor over the life cycle of your service. Monitoring is not only about observing system behavior, but also understanding it. You really want to have insight into what's happening inside your service, not just seeing that it's okay, it's processing some number of transactions, but what's it doing under the covers so that you know if something goes wrong, what's actually happening under the hood. And so when you're doing something as complicated as migrating from one environment to another, you want to ensure that you have the right monitoring strategy way before you actually start doing the migration. So you saw that Planet actually started using SignalFx a couple of years before they actually finished their migration. And the reason you want to do this is you want to move as few things, you want to change as few things as possible when you actually do this migration. You want to establish all the baselines and have all the observability that you need way before you actually execute the migration. And it's a good opportunity to use your upcoming GCP migration as a forcing function to ensure that you're kind of putting all the right monitoring best practices in your organization, the right philosophy of observability, and having the right tooling and the right products in place for you to ensure that you understand what your system is actually doing. So the first class observability, once you have it, is not only going to help you manage this migration, but it'll help you operate your service after you complete the migration. So a few lessons to share about monitoring in general. So there's much more to monitoring than just infrastructure, especially when you're moving from one cloud system to another. So for one thing, like system metrics are not very useful. They are often not even comparable across different cloud environments because, for example, what's an instance type in AWS might not map exactly to what you have in GCP. And so it doesn't really make sense to compare things that aren't really comparable. It's like apples and oranges. But there are some more like systematic problems with using just system metrics. So oftentimes, system metrics do not indicate application performance issues. Your load averages might look fine, your memory utilization might look fine, but your application might actually be struggling for various other reasons. And even when system metrics do indicate system performance issues, they often are not very actionable in the sense they don't tell you what the problem is. They just tell you that there is a problem. So you really need to go beyond system metrics. You want to take what we call a data-driven approach to development and operations. The key insight here is that you cannot understand, you cannot improve, you cannot manage what you don't measure. So you really need to think about measuring all the things that matter to you as a person who's developing an application. What to you characterizes the proper behavior of that application? Even if you have a really simple service, for example, it might be some kind of a lookup service. You get a request to look up something, you look it up in the cache. If it's there in the cache, you can return it. If it's not in the cache, you put it into a queue, and maybe there's a thread pool that pulls stuff off the queue, looks it up in a database, and then returns it. Well, you should be measuring not only the number of requests that you're getting, but you should be measuring the number of cache hits, the number of cache misses, what's the size of your queue, what's the size of your thread pool, what's the utilization on this thread pool. Each of these instrumentation points is hardly like 1 or 2 lines of code, but believe me, it'll pay off in spades when something falls in the pot. So if you are in doubt, instrument. Okay, so the wrong time to wish you had instrumentation is like when you're in the middle of an outage, it's 3 a.m. in the morning, and you wish that you knew what was actually happening over there. You see that things are running slow, but you don't know if it's the database or if it's the cache or what is the problem right there. So a fairly moderately instrumented application, of moderate complexity, it's not unusual for them to even send thousands of metrics per host. It's not unusual. But once you do that, if you have, let's say, 1,000 metrics coming per host, and you have thousands or tens of thousands of instances, you are now looking at millions of time series. And you can't really absorb that kind of information. So you really need to use then analytics to boil all this information down into a small number of KPIs that you can actually absorb. So obviously, you need to be measuring the KPIs, which are what you promise as a service to your clients. So these are the SLAs, the SLOs, the SLIs, that the clients of your service care about. You obviously need to be measuring that because otherwise you cannot guarantee that you're actually meeting any of those objectives. But equally, you should also be measuring the things that you as an application writer care about, right? You should be, for example, if it was that lookup service, I would want to know what's the hit ratio, what's the aggregate hit ratio across the entire tier, what's the 99th percentile of the queue sizes across my entire tier, what's the thread utilization on my thread pools. So there are some small number of metrics that will kind of capture what's happening in your system. If you think about a pilot who's flying a complicated airplane, there's obviously a lot of metrics that are available to that pilot, right? Everything from like various hydraulic pressures and oil temperatures and exhaust gas temperatures and all that stuff. But that's not what's on the pilot's HUD. The pilot is operating the system based on a small number of metrics that are projected onto the head-up display. And yes, if something happens, then yes, they are available to, those other metrics are available to debug and fix the problem. And you need to take that same sort of mentality when you're operating your own applications. So use analytics to take all this complicated information and boil them down to a small number of metrics that you're actually monitoring. Now, second, use your monitoring tools to establish a baseline for system behavior. So this is one of the reasons why you want to set up your monitoring and observability toolchain way before you actually do the migration. What is normal for your system? It's not always a very simple question to answer. So here's a chart of activity in one of SignalFx's own systems. And you can see that it's very strongly periodic. This is activity over a week. So you can see that in the weekdays, there's a lot of activity on the system. During the weekends, it's not so active. And so if somebody came up to me and asked, hey, Rajesh, is 30,000 normal? Well, 30,000 is not normal if it's Sunday afternoon. It's also not normal if it's Monday noon. But it is about normal if it's Monday at 9 a.m. So what is normal would depend a lot on your system. So like this system is, of course, very dependent on weekly behavior. But you can imagine other systems that behave, for example, there might be a warm-up phase when you push a service that your caches are get cold, and so it takes some time for your caches to warm up, and that might be normal for your system. There might be other things where it's very periodic, but on a monthly basis or on a quarterly basis or based on other business activity that might happen in your system. So you want to make sure that you're capturing all these metrics and you have enough baseline in them that when you do your migration, you have something to compare it with. If you've not given yourself enough time to establish that baseline, you're not going to be able to, again, compare and know that if your migrated instances are kind of doing something that is normal. Now, of course, comparing it to past behavior is one notion of what's normal. You might also want to compare it to your other control groups. So if you're migrating from let's say, AWS to GCP, and you have some instances running in GCP, you want to measure apples-to-apples comparison of what is happening on GCP versus what's happening on AWS. And again, here, you don't want to be doing the system metrics. You want to be doing the KPIs and the other metrics that really give you a proper comparison if your system is working well. Now, this whole A versus B is not just like GCP versus AWS, right? It can be, oh, here is my Canary Build, or here's an alternate implementation of an algorithm which I think is going to be much better. Well, is it better? You should be measuring it. That's the only way you're going to know if you actually made an improvement or not. And not just measuring it in a synthetic benchmark, you want to be testing it in production to make sure that it's working as you intend it to work. In this case, we actually pushed out a Canary Build, and you can see that the Canary Build is working very, very different than the rest of the population of the servers. In this case, it was actually an optimization, so it's doing as it was intended. If it was not, we would have caught it within a few seconds or minutes and reverted the canary. So the third thing is that timeliness of metrics and analytics is critical. Okay. So microservices, data sampling frequency, there's a lot that can happen within the span of a few minutes. Like, most of you are familiar with all these like microservice architecture. These are very large, complicated, dynamic systems. They're growing and shrinking. They're auto-provisioning. They're auto-scaling. They're doing a lot of stuff. And a lot can happen within a span of a few minutes. So you may fail to identify patterns and activity by sampling kind of like coarse-grained metrics or things that very, very high latency. Just imagine to continue kind of like the aviation metaphor, imagine a pilot trying to fly an airplane where all the instruments updated once a minute instead of every time they made a change to the controls. But that's what most people are trying to do nowadays. They're trying to operate these very, very large, complicated systems by looking at metrics that operate like once a minute. So low latency real-time monitoring really, really lets you understand how the system behaves when you make changes to them, when you push a canary, when you update a configuration. How does your system really behave? To be able to identify the patterns that happen and to be able to react very quickly when something is happening that you don't expect, or something that you don't understand, or something that should not be happening, to be able to identify those behaviors, react to them, remedy the problem, and verify that your remediations are actually working. So, the way I like to think about it is that your system is telling a very complicated story, and you should be watching the movie and not a slideshow. So this is the value of real-time streaming analytics in terms of ingesting high-resolution, low-latency data and giving you analytic insight instantaneously. So to summarize, make sure that you go beyond infrastructure level metrics, measure all the things that matter to your system. And if you're in doubt, measure. It's always easy to throw data out if you don't need it, but it's impossible to, you can wish as much as you want, you're not going to get the instrumentation in when you need it, when things are falling in the pot. Use analytics, because at this point, you're going to have a whole lot of data. You really need analytics to help you identify aggregate system behavior, identify outliers, deviations from normal behavior, and establish baselines for system behavior and measure in real time, in just at the highest possible resolution with the lowest possible latency for you to kind of operate your system successfully. So Troy is now going to talk us through how Planet Labs did their migration.
So just to kind of touch on some of the metrics that we've used. First of all, I apologize. A lot of the migration we did predated the year back. I can look in the graphs that we have. So most of the graphs are not right during the middle of the migration, but I found some that I think show a lot of the kinds of things that we found during the migration and sort of how we think about it. So I'll dive into a few of these more directly. So this is kind of just to give you an idea of the environment that we were working in during the migration period. So this goes back to July of 2017. In December of 2016, when we started our migration, we had everything running on AWS. We were processing about 300,000 images a day. We had never run more than 20,000 of our worker VMs in the history of the company. And in fact, a couple years before that, we hadn't run more than about 500 of them. So we had been on this ramp for a while. And in the middle of this ramp, right when we launched all of our big satellites, we moved to Google. And this is kind of what happened next, is we went really quickly through this period. So I talked about how we launched a bunch of satellites in January. It actually takes us a while to operationalize those satellites. So those satellites didn't really start coming online until June and July, but you'll see this big shift in our workload as we sort of went through a whole set of things around that period. And then we've kept going over time as we've launched more satellites and gotten more products. We actually hit a new record of 53,000 concurrent VMs running just a few weeks ago. And so this is just kind of a good graph to remind us kind of where we've been and what we've been up to and sort of the scale that we've been able to get on the Google Cloud. Here's another example of where we track API response times. So this is a similar, this is an application level metric, not really a system level metric, but we're tracking just response times and capabilities. So this was actually a new endpoint in our storage system that we have been developing for some new capabilities that our developers wanted to use. And we're tracking it sort of over history, but you'll see that when, we can tell when we flipped the switch, when that started to go, you'll see we found a problem somewhere along the way where we got huge spikes that we caught pretty quickly and then we're able to correct and sort of monitor. So just another example of one of the kind of small things that we watch on our ops teams. This one I think is just a good way of how you can sort of watch changes through the system. And I do wish we could sort of stretch this back to the migration time frame, but this is sort of looking at some metrics of our backend database server for that storage environment that I talked about. So this is an environment that's tracking over 2 billion objects and all the metadata that's associated with that. So we moved it to Google and learned some good lessons about moving big databases that I'll get to later. But one of the big things that we wanted to do was actually leverage Bigtable to manage a lot of our metadata. So we had all this stuff stored in Postgres in a horribly inefficient manner, like just big JSON blobs inside of a Postgres column. If you want to have fun sometime, have 100K JSON blobs in Postgres columns and try to manage that. So we pulled all that data out and put it into Bigtable and flipped the switch on that environment. And again, to track sort of what we wanted, our network utilization the day we flipped the Bigtable switch just dropped. Because all that data stopped coming out of our system and started coming out of Bigtable instead. So this was just like one of those metrics that we could sort of see what was happening during that time frame. Another thing that we did is we used to have an on-disk based backup where we would run PG dump to get our backups, I think PG base backup to do our pieces, but we switched over to actually mounting an extra persistent disk and snapshotting the database to persistent disk and then moving that persistent disk. And you'll see that that new backup popped in our disk activity. So this is actually the instance where we do all of our backups. And so we were getting lots of disk activity until we did the snapshot stuff, and that sort of dropped off. And then I guess the last thing that sort of shows here is we actually, one of the things about Postgres is if you drop a big table or a column, in our case, that was all this JSON data, the storage for that doesn't go away immediately. You actually have to dump and restore the database to get it away. So the performance came down in the network bandwidth, but that was all, the disk utilization was still there in the system. So we decided we would build a brand new, go from a 9.3 server to a 9.5 server, do a dump and import of the database. And as things sort of happened, this was the first try. it didn't work, which is kind of why we see some spikes and then everything goes back to normal. But we figured out why it didn't work, and a few months later, pulled the trigger again and sort of got to watch. We'll see a new database server, but we were able to do a before and after comparison of the old to the new to make sure that the statistics lined up, and certainly didn't get any worse than it did before. So I think it just sort of, this is obviously over a very long period of time, so it's not what we use operationally, but it's great to tell the story. Or maybe this is our version of the movie of what happens to big Postgres databases at Planet. It is very useful for us. Another big thing that we get out of our environment that we love is the fact that our AWS platform, our monitoring and visibility looks exactly like our GCP. So I mentioned that we're moving these Kubernetes environments back and forth. So we use an internal tooling system called K2 to deploy Kubernetes into AWS. And that K2 platform, we name again, we're really good at naming, we name all of our clusters KK something. In Google, we moved to using Terraform to deploy all of our stuff. We actually got kind of creative. We call that tool Teraflop, which is a little more interesting than Terraform, but it's all TFK. So you'll see up here we get a common view of both our Google clusters right next to our AWS clusters as we're sort of walking through this environment. And that goes even deeper. This is an example of our dashboard for one of our clusters. So this is a Google cluster. These are the variety of metrics that our standard ops guys use. But this looks exactly the same for our AWS clusters as it does for our Google clusters. So if we get a page in the middle of the night, and we don't get those, but I hear people do, when they wake up at 3 a.m., they're not having to go like, oh, which environment I am and what signals am I looking for? They see a lot of consistency. I will say the one difference, if I showed you the snapshot, is those two top lines would be blank in AWS because we've moved to a service mesh Linkerd-based ingress, and we don't have that in AWS, but we've left the format the same so that the visibility to the ops guys is also consistent. So with that as kind of an overview, I thought what maybe the most valuable thing, rather than to get into the nitty-gritty, or at least maybe provide some context for the nitty-gritty, is to share with you some things that I think we learned at Planet about doing a migration of this kind of scale, both about how to do them and maybe some things about Google Cloud in the process. So my number one recommendation to anybody doing a migration like this is don't change anything you don't have to change. So I'll come back to that second. So I guess the first thing actually before that, I sometimes take this for granted, and I almost forgot we put this in the slide, but the planning part is actually essential. We were in a hurry, but we took a lot of time to evaluate the move, make sure it was the right move. Maybe more importantly, we locked ourselves into a conference room in San Antonio for like a week to think of all the things that could go wrong and how we wanted to do this and have a lot of debates. That time up front, even though we felt a lot of pressure to move fast, was invaluable in the process. So don't shortchange yourself on thinking about this stuff ahead of time and asking all the crazy questions, which will never be all the questions you will find, but you'll find that some of those were really helpful. The second thing, and the one that probably rings the truest for me, because we didn't do this everywhere, is change as few things as possible. It's super tempting, and we fell into this in a couple of places, but to want to fix all the problems of your service and your app while you're migrating. I'm on an old version of Ansible. I don't want to use that anymore. I want to get off of Postgres. Let's move to Bigtable while we move to Google. Let's containerize everything. We'll go from Ansible-based VMs in AWS to containerized new solution in GCP. Resist that temptation. It makes the migration way more complicated, and I guarantee you it will take you 3 times longer to move if you do that than if you move and then make the change. And so my recommendation is to avoid that. So we moved the biggest part of our infrastructure, probably 75% of our servers and applications in 90 days, and the last 20% that we're moving over has taken us 18 months. Because it's gotten much more predictable. People are changing lots of things. The refactoring that they want to do before they move never quite finishes. And it just sort of drags out because it's much harder to bracket, I think, things around that. That worked for us. Like, I think in particular, had we tried to take our 20 terabyte Postgres database and migrate to Bigtable while we're going to GCP, the problem is more things are going to break, and it's more confusing what broke. Did it break because Bigtable didn't work for our application? Did it break because the Google Cloud is different? Did it break because our VPNs didn't work? Like all of those things just get more complicated. So I think in some ways, it's kind of the antithesis of sort of a microservices or maybe a CI sort of incremental change approach. The more you bake into the change, the more complicated it's going to be, the more likely you're going to fail, and it's actually going to take you more time. Another big thing, you heard me sort of talk about this, and I'll get into some details, but data gravity is real. It seems like if you're looking at migrating, particularly from something like AWS to GCP, it seems like the two most similar things on the planet are S3 and GCS. So it's easy to just kind of go like, oh, I got a bunch of data in S3, I'm just going to copy that data to GCS. The problem is when you start doing things, and not everybody does this on this scale, but when you start talking about moving 7 petabytes of data, it turns out there's not an O'Reilly book that is very good about how to move 7 petabytes of data. So we started by doing some tests. I took a database that was on AWS, and I did a base backup to GCP. And I was totally blown away by how fast the backup was and thought, wow, this whole data copying thing is going to be easy. The problem is one database backup doesn't simulate moving 2 billion objects from GCS that was all in one bucket, I would say, and I can talk to you about why that is, but we had one bucket with like multi-billions of objects that we were trying to move over. And so we did this testing. We thought the pipes are big because it turns out like, the advertisers and the ads are all sort of going between those two networks. So both Amazon and Google are set up to do that. But it turns out we use there's a cloud migration tool that Google has that's actually quite good. So we flipped that on, we pointed at the bucket, we started running our tests, and we're like, wow, we're going to be here for 6 months if this happens. And so we sat down with the Google team, and we figured out that part of it is they're sort of serially going through our key space, object by object, doing these lookups, moving this data over. And so what we ended up doing, to make a long story a little bit shorter, is that we worked with Google and how our thing was set up, and we ended up running 32 separate simultaneous migration jobs by dividing up the key space. We had a pretty distributed key space. We use MD5 sums of all of our images to be the main storing place, so it was widely spread, and we literally just took that key space set, divided it into 32 groups, and then put those key spaces into 32 separate migration jobs and flipped the switch, and 21 days later, 7.5 petabytes of data was moved. So you can do it, but you have to know that it's probably, like what we did doesn't work for everybody else. There's different ways to approach it. I would also say probably the other interesting story that we had to move over was the Postgres database. So we have a series of RDS databases, but we also had these larger databases that were self-managed Postgres instances. And we thought the simple thing to do would just be able to create a read-only replica of our Postgres database in Google. So we tried to do that, and one of the problems that we ran into was that we did everything inside of Planet on private networks. We have regulatory requirements and other sort of security things that keeps everything without a public IP. So our databases in AWS had no public IP, so it was basically VPN connected, and we just couldn't get latency throughput to keep up with our database performance to create a replica in GCP running across VPNs. What we ended up doing that actually worked quite well was we took an elastic IP in AWS, assigned it to the database that we had, and ran our replication across the public network for the 2 or 3 weeks where we were replicating into GCP. And it turns out the public network latencies weren't as constrained as VPNs. We actually got that to work. And so we were running for a long time with a replica in GCP off of our primary database in AWS. The thing that we missed was we got so comfortable with that, and I was going to embarrass the guy on the team who was here because he was going to show up, but he must have known I was going to talk about him. Anyway, he got sick. Our main DBA got sick. We all took our eyes. We actually had a graph that showed our replication stats. We took our eye off the ball. We basically got everything moved over and ready to flip the switch from that being the replica to being the primary, and we had some network latency over the weekend before we did it that caused our other one to get out of sync. And we ended up having to wait 2 extra days while the database caught back up, and we sort of got that solved and flipped the switch. So we kind of did part of the migration on a Friday, figured out it wasn't going to work, came back in Monday morning, the replica had caught up, we flipped it and went the rest of the way. which was good because Will was on stage at Next the Tuesday after that. But we got it all done on time. So I just think the whole data thing actually turned out to be quite hard. We think about things like Bigtable and these sort of systems that are very different, but actually it's the things that look the same that aren't quite the same that are the most complicated parts about a move like this. So for us, I think if you're coming from an AWS to Google environment, the biggest challenges for us were to understand networking. You kind of think networking is networking, TCP is TCP, but I will say this is an area where the two environments are probably the most different. And I don't even, well, I don't know. My team will pick one that's better or worse. I don't even know that it's better or worse. They're just different, and it's helpful to know what some of those are. Probably the biggest thing for us, and this is getting better, I mean, I talked a little bit about the need for the VPNs. Just how to set those up. Like VPNs are set up different in AWS than they are in GCP. Once you've kind of figured out how to pair them and set them up, they work very well. We still do a lot of back and forth. We have a huge amount of traffic going between the two clouds over VPN, and that's worked well for us. Google's use of SDN is really powerful and extremely performant, but causes some things you just don't quite expect sometimes. For us, it had to do with things like, first of all, the internal load balancer at Google is actually not a load balancer like you think of it. It's not like an HA proxy or some kind of load balancer instance that looks like a device. It's actually forwarding rules in the network that just moves traffic around. So they call it a load balancer, but it's really a combination of front-end and back-end forwarding rules in the network. That means you can't do things like terminate SSL at the load balancer internally. Because it's really just moving traffic to your back-end devices, all of which works fine. It's just different, and that was hard for us to get used to. Some of the internal shared, it's called shared VPC. I keep wanting to call it XPN. A few Googles will probably remember it as XPN before it became public, but the shared VPC XPN stuff was really early for us. It's still kind of early. Like we didn't know early on that you couldn't expect to have the internal load balancer not work across a VPN. Because it's just a device. Networking devices should be available anywhere. But when you dig in, you understand why that is, and we found ways to sort of work around that, and that all works very well for us. I think also private DNS was a thing that was missing when we moved. It is being tested now. We're actively testing and hoping to move to private zone resolution inside of Google. And so all these things I think work fine. They're just different, and you need to be aware of them as you're sort of thinking through how you're going to do things. So I guess in summary for us, look, our migration went really well. We're running a massive amount of stuff in Google. It's going great. We're moving new stuff over every day. We are going to maintain a two-cloud. Actually, I guess technically we have some stuff in Azure. We'll be in AWS for our regulatory environment that has to be in GovCloud. But we're also digging in a lot. Mentioned heavy use of Bigtable, Cloud Memory Store. A lot of the new services that are coming out, we're trying to migrate and sort of embed to, even as we grow. We are focused a lot on Kubernetes and service mesh approaches. I will say that partly because of this private networking mismatch, partly because of just some experience we have in running Kubernetes, we run self-hosted Kubernetes in Google. We continue to evaluate GK as an option, but we actually have our own Kubernetes deployment that we run and manage, and that has worked well for us. And actually, we can piggyback on a lot of GKE capabilities that have been put into the public use for us to do things like access underlying IAM roles in our instances and credentialing and so forth. A lot of work with the move towards analytics to incorporate GPUs and TPUs into our infrastructure, both in the Kubernetes side and in other places. And then there's just this constant effort on our part to balance cost and speed, take advantage of preemptible VMs, understand what the best patterns are for distributing our imagery and managing egress costs. And so that's what keeps us busy going forward now that we've survived the basis of the migration, and we're really sort of excited about that.